Let me move to the final speaker of this morning session. My welcome to Giuliana Siddi from CRS4, who is going to talk about gravity data inversion with a Adiabatic quantum computer. So thank you so much for having accepted our invitation. Giuliana, you can start to share your screen. You already sharing. Beautiful. You can share your slides as well.
Okay, let's try to find the
I think that it is the Sebastiano's screen. So
sorry. Sorry. Okay, now there
Can you see my slides?
Yes, we can. So the floor is yours. Thank you.
Okay, thank you very much, Enrico. Hello, everybody. My name is Giuliana Siddi Moreau from the QC group of CRS4 Research Center. Let me thank CNR and Cineca for this opportunity of being here at HPCQC 2021. I would like to present some preliminary results on this ongoing work involving me, my co-workers Lorenzo Pisani, Andrea Mameli, and Carlo Podda, our head Giacomo Cao, and our mentor Enrico Prati. And we acknowledge the Cineca Award under the ISCRA initiative for the availability of adiabatic quantum computing resources and support. Let me thank Daniele Ottaviani and all Cineca staff for granting access to QC devices, namely the wave annealers. This is truly a blessing for the overall Italian research community. So, let me see. Can you see my screen? Yes.
We can see the first slide.
Okay, I'm trying to. Okay.
Okay, now it's in a slideshow.
Okay,
Great.
Right. So, for those who don't know CRS4, it is a research center located in Italy, in Sardinia, that boasts 30 years of activity, mainly focused on R&D and HPC applied to many fields. And we are located in the scientific park of Pula. Here are some nice shots of our venue. The quantum computing group is relatively young. It has started its activities in December 2020, with the main goal of making quantum computing go out of the lab and to apply it in the areas of expertise of our research center. So let's see a quick outline of the presentation. We will give some background of the gravity method. We will illustrate the framework of the forward and the inverse problem. After that, we will cover the formulation of the quadratic unconstrained binary optimization problem, and we will show some preliminary results on the wave annealers for 2D and 3D inversion for pointwise density anomalies. Gravity method is an important geophysical tool for subsurface mapping of the density distribution. One of the main advantages is that it is passive. In comparison with seismic method, you don't need to provide energy to the system to get an image that collects meaningful information about the structure of the subsoil. Since the 80s, the development of better instrumentation have made the large-scale airborne gravity survey become possible. Despite their potential, gravity sensors are not used very often in geophysics. Spring-based gravity methods are already very sensitive, but their measures can be affected by errors induced by vibrational noise. Quantum gravity meters are not affected by vibrational noise, so we are prone to consider their development as a new dawn for gravity method studies. The gravity field of the surface of the Earth is not uniformly the same everywhere. It varies with the distribution of the mass material below. As you can see in the image, the self-dome is less dense and induces a negative local anomaly on the vertical component of the gravity acceleration. This change can be measured and interpreted in terms of likely causative geology. The higher the gravity values, the denser the rock beneath. Gravity data cannot be used as they are to illustrate this fact. we can see some images of the satellite acquisition of gravity data. These images were acquired on GOSE mission by European Space Agency. Gravity varies over time at a specific location for several reasons: instrument, tidal effects, ground vibration. It varies with latitude due to the change in diameter of the Earth and the variation of centrifugal acceleration. Gravity correction involves reducing the effects of this feature of Earth planetary gravity in order to isolate the effects of lateral variation in mass. These corrections are not a trivial exercise. Some of the ones we apply to the raw gravity data are mathematically complex. So regardless if the data is being collected by satellites or by terrestrial devices, gravity data must undergo too many corrections, such as free air, atmospheric mass, Bouguer. At the end of the story, we get a gravity anomaly map at the surface, like this one on the right, no, on the left. And we want to obtain an image of the structure of the subsoil. Let's now inspect the forward problem from the mathematical point of view. So if we consider a domain filled by some density distribution, the gravity method stems from Newton's laws of universal gravitation, which is equivalent to solving a Poisson equation for the scalar gravity potential U. If we know the subsurface distribution of density anomalies through the forward problem, we can evaluate the gravity field at the surface. The Poisson equation is a nice Laplacian, hence it's linear, and we can reformulate the problem as a gravity anomaly imprint created by a distribution of subsoil density contrast with respect to a known background density. This density contrast is described by a function sigma that we'll see here in this slide. So here is the forward problem to evaluate the gravity anomaly given the density contrast distribution. The most common approach is to solve it in an integral way using green formulas or Plouffe integrals that appear to shape this S contribution in the slides. We discretize the Earth model into a set of rectangular prism or voxels and consider that each prism has a constant density. We can evaluate the resulting gravity synthetic acquisition at the top surface. To express the forward problem framework to quantum computing implementation, we can write the formula seen before by means of a binary formulation. The density constant contribution sigma of X voxel is turned on and off by an appropriate binary variable tau. So the gravity anomaly at the top surface is expressed as a weighted summation of binary variables. But what about performing gravity inversion in a stent? Given the observed gravity fields at the surface, we want to discover the density within each cell of the surface discretization. Unfortunately, it is an ill-posed problem. A well-posed problem, according to Jacques Hadamard, has the properties that the solution exists, the solution is unique, and the solution's behavior changes continuously with the initial conditions. Laplace problem with boundary conditions defines that the overall boundary is well posed. However, we don't have observation of the gravity field vector at the sixth phase of the computational regions. And moreover, often we have only the vertical component of the gravity vector. If we are lucky, it's special derivative. Thus, our inversion problem is ill-posed. It admits more than one solution. If the problem is well posed, then we have a good chance of solving it on a computer using a stable algorithm. If it is ill posed, it needs to be reformulated for numerical treatment. So to do so, additional assumptions are used, such as smoothness of the solution, for instance, with the Tikhonov regularization. Instead of making such assumptions to ensure sharp density discontinuities, we choose the framework of compact gravity inversion, thus introducing suitable constraints to restrain the space of candidate solution. Moreover, the inversion problem workflow is casted as an optimization problem. We perform the minimization of the loss function that takes into account the difference of observed and computed gravity data at the acquisition phase. And this minimization implies a loop including forward problem evaluation on a tentative density distribution, backpropagation of the residual, and then the update of the tentative density distribution according to this residual. This collection of steps has to be repeatedly computed until convergence. As in inversion, we found loss functions that are far from being convex and featuring many local minima. Conjugate gradient-like methods are likely to get stuck in local minima. To overcome this fact, iterative optimization methods are employed, and a large number of iterations are carried out to explore the relevant part of the solution space. We are never completely sure that the best solution we get with our numerical method is the good one. So this iterative inversion tends to be computationally cumbersome. So this aspect leads the motivations of our study of gravity data inversion with adiabatic quantum computers. Because first of all, the adiabatic quantum annihilers find the minimum of an energy in landscape. We have to define only the proper Hamiltonian. And we are dealing with a problem whose non-uniqueness is caused by the nature of the physics and the underdetermination of the problem. And the solution that we get as a minimum of the energy landscape might be good, at least as good as the solution we obtain with on conventional hardware with the iterative methods or other methods like genetic methods. And moreover, we can embed in the loss function the forward problem evaluation, and this speeds up the procedure. Our concern are to give a good representation of the problem Hamiltonian, gathering all data we can use to reduce underdetermination, gravity acceleration, its spatial derivatives that are components of the gravimetric tensor, stabilization terms to get a compact solution, binary constraints coming from other kinds of surveys, has the position of the top of the density anomaly that often is known. As we want to feed the D-wave quantum processing unit with our loss function, we write the problem as a quadratic unconstrained binary optimization one. Then, if we assume that we have a single density constraint, we know how to write a forward modeling problem, and we embed it in the objective function. The data misfit at the acquisition point is imposed in a least square fashion. We add as well an additional functional which embodies the principle of minimization of the volume of the density discontinuity. The problem of imposing constraints using Lagrangian penalties is that we have to tune the selection of the value of the Lagrangian terms that are used to enforce the constraint. Grid search has shown to be ineffective for this problem, as the lambda value is extremely case dependent. So we have chosen to bind the Lagrangian coefficient lambda to the value of the L1 norm of the residual between gravity and synthetic observation at the acquisition surface via a simple gradient descent in order to have a reasonable value in several iterations. So here we can see some preliminary results in 2D. We have the target model on the left, on the XZ plane, on which we have computed the synthetic section at the top of the domain for the vertical component of gravity acceleration GZ, for its spatial derivative along the x-axis that we denote as TZX, and for its spatial derivative along the z-axis that we label as TZZ. The three images correspond to the inversion result for the three independent inversion processes, respectively fed by GZ, TZX, and TZZ synthetic acquisition at the top line. Each of the variables have different green functions and different cost function representation as far as the forward model is concerned. And the optimal value for the lambdas is computed with the gradient iteration I mentioned before. Two low values for lambda correspond to empty solutions, denoted with the red dot in the graph below. Obviously, the annealing process trying to minimize the number of binary variables that produce the gravity anomaly at the surface. So when the binary quadratic form does not provide a valid solution, it gives back the null solution that truly minimizes the shape minimization function.
Okay, Giuliana, you have 1 minute left.
Okay, so let's keep, we have tried so far with the Adiabatic system and the 2000Q system, and we have varied the sampler and we get the same results. We have also tested the 3D procedure relying of GZ and 3 gradiometric tensor component. And we have the result of the pointwise anomaly. We have recovered the correct position, both for deep targets and with shallow targets. There is a mistake on an image, but anyway, it was correctly recovered. So now we are currently working on more complex density anomalies, and it is a really interesting benchmark to assess whether locality issues might affect the solution. And so thank you for your attention, and thank you again to Cineka for these initiatives that awards us of computational time in the D-Wave annealers. Thank you.
Thank you so much. Let me see if there is any questions from the audience. Let me ask you just a very quick question. Is your feeling that you are mainly constrained by the topology of the hardware or by the difficulty of mapping your specific problem on a Kubo?
Well, there are both aspects and a third one, because the compact gravity inversion has also a problem of floating solutions. So to avoid this, there are several formulations in literature that give appropriate weights to have a correct target recovery. So And on one hand, we have to find the right formulation that complies to the QBO implementation, because the sensitivity, the float sensitivity is different with respect with conventional hardware. On the other hand, as we have a quadratic form, and that gives rise to full quadratic matrices, we have to play with the cutout of the terms to be sure to have all meaningful terms included for the physics of the equation.
Thank you so much for having shared these results and for having accepted our invitation. Let me also mention that in turn, my group is taking advantage of the ISCRA-C grant. So let me officially and publicly thank Sineca for that. So Daniel, we are done for the session of this morning. We are going to meet again at 2 p.m. with a very amazing and intense new session with the companies.
Exactly, Enrico. Thank you for your kind words about the ISCRA project. Also, thanks to all the speakers that have spoken this morning. It was a very interesting session. And yes, we will see again in 1 hour and 7 minutes for the precision, and with a new session with software and hardware manufacturers. Thanks a lot. See you later.
See you later.